Hi, everyone. Welcome back to the podcast Exploring the Cosmic Files with me, Rishabh here. If you can remember my last episode, I had talked about the different types of subatomic particles, different fields, and forces. We have seen that there are different categories of subatomic particles, such as the quarks, leptons, and bosons. We have also discussed about different fields, which are of two types, the matter fields and the force fields. Then we talked about the four fundamental forces, which are, drumroll please, the strong and weak nuclear forces, the electromagnetic force, and gravity. Today, I will talk about a special subatomic particle called the Higgs boson, and also the field which creates it, called the Higgs field. So, without a question, one of the most scientific breakthroughs in the 21st century was the discovery of a particle at the CERN laboratory that possibly be identified as the famous Higgs boson, named after a physicist named Peter Higgs. This boson was created when they smashed two particles together. This is sometimes naturally made by something called the Higgs field. The Higgs boson is formed in the Higgs field just like how a hump is formed when you jerk a rope. Now, you might be thinking, what exactly is the Higgs field? Well, this field is thought to give mass to all particles who interact with it. But the Higgs field is neither a matter field because it does not create particles that make up matter, nor even a force field, even though it creates a boson. But the Higgs boson isn't an ordinary boson. The Higgs field isn't a force field, also because it cannot accelerate particles, or it does not transfer any kind of energy. So it is a completely different field altogether. But you might be thinking, how exactly does this field give mass to other particles? Well, no need to worry. You're not alone. In 1933, a challenge was proposed to a bunch of expert physicists to understand a simple way to help the common folk grasp all this Higgs stuff. This challenge was proposed by the British Science Minister, and the winner of this challenge had a very simple explanation for this. I will use a more modern example to explain the working of the Higgs field and the Higgs boson. So imagine that there is a New Year's party and there is a big crowd of people, evenly spread out and having some fun. In this example, the crowd represents the Higgs field. Now, let's say a famous actor, like Tom Cruise, for example, walks into the room. Everyone would want to get his autograph and take a selfie with him. So he will be surrounded by the whole crowd. And since people are continuously interacting with him, he won't be able to get to the other side of the room. Now, let us say his assistant walks into the same room. Do you think the crowd will want to interact with the assistant like how they interacted with Tom Cruise? Obviously not. No one would want to interact with him. Poor guy. So he can move through the party without any effort because no one is interacting with him and no one is willing to interact with him. The assistant in this example would represent a particle that does not interact with the Higgs field. Thus, it will be massless. So it will move very fast. Tom Cruise, however, represents a particle which continuously interacts with the field and will gain a lot of mass and therefore move very slowly. So now, particles with more mass move slowly, and particles with little mass move faster. But now you might be wondering how the Higgs boson fits into any of this. Well, there is a simple explanation for this too. Now, let's say that the security guard at the door announces a rumor that Robert Downey Jr. or the actor of Iron Man is going to make an appearance very soon. At the party, the people closer to the door will hear it first and come closer to get more details. After that, the crowd spreads out and relays this news again to the people nearby. They again clump together to hear the news and disperse to form new clumps to pass on the news through the crowd, and the cycle repeats again and again until finally Tom Cruise would hear the news at the end of the room. This clump represents the Higgs boson. Now remember that in the first example, the assistant and Tom Cruise have zero mass before they enter the room. So that means only when they interact with the crowd do they gain or lose mass. So that means particles will gain more mass the more they interact with the field. And the Higgs boson is like a rumor spreading through the crowd. Now, this analogy is just that, an analogy. But it is the best analogy so far. And these kind of analogies will help the common man understand the seemingly complex, yet simple, world of quantum physics and mechanics. Tune in next time for more of similar talks. Thanks for listening.